Hi class, welcome back. So we're going to try example number 5. We're going to analyze the graph of the function and determine any of the following characteristics of the graph. We're going to type DNE if the answer does not exist for any of the characteristics below. So let's begin with domain. In general, right, every function domain is all real numbers except what makes the function be undefined, right? So what values of x makes this function be undefined? By looking at this, it's going to be whenever the denominator is 0, because that will be making anything 0 on the denominator makes the function undefined. So basically it will happen whenever x squared minus 1 is equal to 0, which happens when x squared equals 1, right? By adding 1, adding 1. And then this follows by taking the square root on both sides of the equation, plus or minus. This will give us x equals plus or minus 1. So in other words, these numbers make the denominator be 0. Hence, makes the function undefined. And the domain is all the real numbers that make the function defined. So in other words, it's going to be all real numbers except -1 and 1. So if you think about it, it's going to be something like this, right? All real numbers except -1 and 1. So if you create this little number line, kind of gives you a nice hint of what to write. So it'll be the interval from -infinity to -1, jump from -1 to 1, jump from 1 to infinity, right? So it's going to be this part. All right, so let's jump into the x-intercept. All right, so the x-intercept can be found when y equals 0 and you're looking for x. So let's set the function equal to 0, right? Let me change the color so that we can see that what we're doing here is setting this equal to 0 for the purpose of putting a constraint and finding when this is going to be 0. For y values of x, well, I have mentioned this before, that the only way that a quotient is going to be 0 is whenever the numerator is 0, right? So this is going to happen when x equals 0. So that's your x-intercept. So 0, 0. The other one, right? The other way will be to find the y-intercept. This is gonna happen when x equals 0. We're gonna find y. Well, what we're gonna do here is we're gonna replace every x with 0, which gives us 0 over -1, which is 0. So in other words, 0, 0. But we already had it, right? So it's the same point. The x-intercept happens to be also the y-intercept. And that's pretty much it for that part, right? Let's find whether the function has a symmetry or not. So I remind you that what we did before is we take the original function and then we replace it with negative x. So negative x, negative x, negative x, right? And let's see what happens. Well, on the numerator, we're going to get negative x. The denominator, negative x squared, is going to be x squared minus 1. If you notice this, we can factor this negative in front, which gives us, if you notice, the original function times -1. That when that happens, right? We talked about this earlier in the other videos. Whenever this happens, this implies that there's a symmetry in the origin. Right. So we have found a symmetry in the origin. Let's talk about now the horizontal asymptote and the vertical asymptote. The horizontal asymptote is the end behavior of the function. So as x goes to infinity, let's see what happens to the function. So what we're going to do here is we're going to do some math here, and we're going to divide both the numerator and the denominator by the highest, by the term, by the variable term with the highest power, right? X squared, right? So we're going to divide both top and bottom by x squared. And we can do this because technically we're multiplying this by 1 over x squared, multiplying this by 1 over x squared. So this means that we end up getting, as x goes to infinity, we get 1 over x in the numerator. The denominator, this gives us 1, and then this one stays the same. So when we apply the limit, right, as x goes to infinity, 1 over a number that is approaching infinity, right? This is becoming very big. This is staying the same. So 1 over a number that's becoming very small, very large. This is going to infinity. I'm sorry, this is going to 0. Sorry, I meant 0. This goes to infinity. Then this whole thing goes to 0. Same thing happens with this. This is going to 0. So what we have here is 0 over 1 minus 0, which is 0 over 1, which is 0. With a similar argument, we're going to say that the limit of f of x as x goes to negative infinity is going to be the limit as x goes to negative infinity, 1 over x over 1 minus 1 over x squared. As x goes to negative infinity, this is becoming very is going down to negative infinity. So this is becoming is going to be a 0, right? It's going to be a 0. The same thing with this one. Sorry, so it'd be 1 over negative infinity square, which is, this is going to 0. So we end up getting 0 over 1 minus 0, which is 0 over 1, which is 0. So because of this, they're both going the same direction. Horizontal asymptote will be y equals 0. So this is a horizontal asymptote. For the vertical asymptote, what we're going to do is we're going to look at the denominator and set equal to 0, right? So the denominator in this case happens to be x squared minus 1. So let's take x squared minus 1, set equal to 0. We've done this before, right? Up here, we have found when the denominator is 0, somewhere in there. So we already know that x is going to be plus or minus 1. So the vertical asymptote will be plus or minus 1. All right, so let's keep those in mind. We have a vertical asymptote, we have a horizontal asymptote. All right, so now let's find the intervals for which the function is increasing and decreasing. So let's look at the first derivative, right? So because we're looking for increasing, decreasing, we're going to find out the values of x that makes the derivative be 0 or undefined. So that's the reason why we're going to take the derivative. And maybe let's write down the original function first, so we can see it. I believe it's x over x squared minus 1. Alright, so if we take the first derivative of this, we have to use quotient rule, right? This is the numerator and this is the denominator. So following our formula is going to be like this. There you go, right? And then we'll take the derivative of x, which is 1, times x squared minus 1, minus x. The derivative of x squared minus 1 is 2x. all over x squared minus 1 square. We're not going to touch the denominator. We're just going to leave it as it is. Then this gives us x squared minus 1 minus 2x squared. And we're going to simplify this because the x squared and the minus 2x squared are like terms. Because they both have a negative, we can factor it out. And that's a mistake here, typo. That's supposed to be x squared minus 2x squared is going to be negative 1x. So let's factor that the negative, so it's going to leave us with x squared plus 1 over x squared minus 1 square. So that's your first derivative. All right. Are we going to have enough space here? Yep. Okay. So we're looking for increasing, decreasing. And this implies that we're going to look for critical numbers, right? So at this time, let's look at when this is going to be equal to 0, right? Let's look at this. So the first derivative is this one right here. When would this equal 0? As we mentioned before, this whole thing is going to equal 0 whenever the numerator is 0, right? Whenever the numerator is 0. But as you guys can see here, x squared plus 1 is never going to equal 0. Why? Because this is a positive number. You're adding a positive number. Positive plus positive gives you a positive number. That's not a 0 number. You already have 1, right? The only way that you can get 0 is that this is negative 1. But we can see that's impossible. This can never be negative 1 because the square makes everything positive, right? That's a quick argument, right? But we can also solve for x by subtracting 1, but then taking the square root on both sides. Well, we already know that you're taking the square root of a negative number, which is going to give us an imaginary number, and imaginary numbers are not real numbers, right? So this does not work, right? So there's maybe this case. So let's check that one out. Can this be, so when can this be undefined? This will be undefined whenever the denominator is 0. So let's take the denominator and set it equal to 0. We've done this so many times already, right? This is going to, the only way that this is going to be 0 is that you're squaring a 0 number. So we're saying that x squared minus 1 has to be a 0 in order for this to be 0. But we already done this before, right? This is going to be the case where x equals plus or minus 1, right? We done this at the beginning, right? We did that problem like right here. All right, so we have two possible critical numbers. We still got to check whether this is going to be a critical number or not. Are these critical numbers? And the answer is no. These are not critical numbers because they're not part of the domain. Remember that we excluded positive 1 and negative 1. So even though it satisfies this condition, the other thing that needs to satisfy is that they need to be part of the domain. Nevertheless, we're still going to use them, right? They're not critical numbers, but they're still going to be useful in the number line. So let's use the number line. And we're going to separate it by using negative 1 and 1. And the first derivative of this, we know this is going to be undefined, right? All right, so we're going to test numbers that are on the left side, such as negative 2, 0, and 2. And so let's look at the original derivative. And as I show you guys in the other video, we can make this check much faster, right? We can say we're gonna check prime of negative 2, f prime of 0, f prime of 2. But here's a trick. Here's a technique. If we look at over here, right, and we look at what we have, we don't need to do too much work, because we already established that these are positive numbers, right? Because you have a positive number, add a positive number, right? Ignoring this for a second. And then we know that the bottom part is also going to be a positive number, because no matter what this could be a negative or a positive, but when you square it, it's going to turn everything to be a positive. So therefore, you have a positive over a positive, which gives you a positive number. But then you have a negative in front of it, right? It's like imaginary negative 1. So you have a positive times a negative. This will give us a negative, like this, right? So what I'm arguing here is no matter what you plug in, this is always going to be negative, 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 right? So by using some logic, right, we're able to conclude that this is negative, 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 negative. So the function, this translates to the function to be decreasing, 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 right? So, right, so then we have that the function is decreasing from negative infinity all the way to negative 1, from negative 1 to 1, and from 1 to positive infinity. And then is increasing does not exist, right? There you go. Okay, so I hope that one's helpful. Next part is to find local max, local min. We can argue there are no critical numbers, right? There are no critical numbers, so there's no local max, no local min. All right, so the next part is to find the concavity and inflection points of this. I remind you that we're gonna these are found by finding x such that f double prime of x equals 0, or f double prime is undefined. So obviously we need to find the second derivative. So this one is gonna be a little hands-on, right? So this is gonna take some time here. Let's again find first. Let's rewrite the first derivative function. Okay. So to find the second derivative of this, let's go ahead and apply which rule? The quotient rule, right? So here we go. We can sort of isolate this, just carry it over this negative. All right, so we're gonna take the top, take the derivative of the top, and leave this the bottom as it is. Minus, leave the top as it is. Multiply by the derivative of the bottom. And then take the derivative of the bottom. Okay, and then we'll take the derivatives now. The derivative of the first factor is going to be 2x. And then carry everything else. The derivative of this one right here is we're going to have to use chain rule because we have a function inside a function. So bring down the power. Leave the inside as it is. Take away 1 from the power. And then that becomes 1. And then multiply by the derivative of the inside, right? Derivative of the inside. The derivative of x squared minus 1 is 2x. And then the bottom part, I did a boo-boo on the bottom part. That's not supposed to be prime. That's supposed to just be square. So I'll make a note here. Make a boo-boo. boo boo. Here is supposed to be square, not prime, right? So that becomes to the fourth power. There you go. All right, so here what we need to do is to simplify a little bit, because we need to figure out the values of x that makes this 0 or undefined. So it makes it easier if we factor this out. And to factor this out is very consistent with what the approach that we've done before. So let me zoom in again. So we're going to look at the factors. How many factors do we have? So here's one factor minus the other factor. So sorry, two terms, right? I meant terms. So this is one term minus the second term, right? And then in this first term, you have what do we have in common with the other term? We have the x squared minus 1 as a common factor. We also have a 2x here and a 2x there. So this one has an extra x squared minus 1, but we're gonna be able to factor. We're gonna be able to factor that much, right? So I'm gonna write it in blue. We're gonna factor a 2x. We're also gonna factor an one of the x squared minus 1 from the first term. So what's left behind? What's left behind from here after you remove this one and after you remove one of them? Then you're left with one of these. Right, so it'll be x squared minus 1. I could put the parentheses, but since there's nothing in front of it, and this is power to the power of 1, we can just leave it as x squared minus 1. Followed by the minus, and then followed by x squared times 2, right? So 2 times x squared plus 1. So this and this, right? Because we removed these two, we factored these two. Let's close the bracket. And since we already factored one of them, we're going to be able to factor one of them in the denominator as well. So there you go. Because here these two can cancel each other out. And so we're left with minus 2x. And then see, we can simplify this here. So you have a minus, right? And you have a minus and a 2. So negative 2 times x squared minus 2x squared. Negative 2 plus 1 is minus 2. So we can combine a few things here, like such as negative 2x squared with x squared. That's going to give us negative x squared. Negative 1 minus 2 is going to be negative 3. And on the denominator, we still have x squared minus 1 to the third power. All right, and we can also maybe factor that negative, right? This negative, we can factor that negative. So, or we can distribute this negative, right? Whichever we want, right? So it would be 2x, x squared minus plus 3, x squared minus 1 to the third power. There you go. Right. So we found the second derivative. It requires a lot of algebra, right? Okay. So there you go. Now we gotta figure out when is this gonna be 0 and for which values this is gonna be undefined. So let's look at the first case. When the second derivative will be 0. This implies, right, we're looking for x values. That makes that true. So this will happen, right? This is going to be 0 whenever the numerator is 0. But this is going to only be 0 whenever 2x, maybe I'll do an extra step here, whenever the numerator is 0. By the zero factor property, we have 2x equals 0, comma, x squared plus 3 equals 0. Now we can argue here real quick that this cannot equal 0. Why? Because you have a positive number and then you're adding another positive number. This needed to be a negative 3 to be able to cancel with the 3 and give you a 0. But x squared is always going to be a positive number, never going to be a negative 3. So that's not going to work. So this allows us to just solve for x here, and we end up getting the x equals 0. So that's one of them. That's a possible critical number. Let's see if it's, we'll finish the other one. Can this be undefined? It's undefined whenever the denominator, this whole thing is going to be undefined whenever the denominator is equal to 0. So let's look at the x squared minus 1 to the third power equal to 0. We know that this is going to be 0 only when the inside is 0, right? Because you're gonna take 0 to the third power to give you 0. So this can only, this should be 0 in order for this whole thing to be 0. Also, you can argue that you can just take the cube root on both sides. That will give us 0, and that will cancel, the cube root will cancel each other, right, with the power. And so we already done this before a few times in this example. So this is going to happen whenever x equals plus or minus 1. But what do we know? These numbers, right, are these part of the domain? They're not, right? The first one, negative 1 and 1, are not part of the domain. But 0 is. So not a critical number. Not a critical number. Maybe red. Not a critical number, but this is a critical number, because this one is part of the domain. But these ones are still useful for us to use in the number line. We actually should be using it in the number line. Alright, so let's begin. Let's create a number line. We have 0, negative 1, 1, x, second derivative. We know this is 0, 0, this is undefined, 0, undefined. So the question is, what's happening around these two, such as negative 2, negative 1/2, 1/2, and 2. Alright, so let's figure this out. So we have to try these problems, right? We're going to test them. Our derivative, second derivative, looks like this. Okay, so we're going to plug in negative 2. And when we plug in negative 2, this turns into a negative. This will always be positive no matter what, right? Because this is always going to be positive. So maybe I'll write myself a note. This is positive always. And then divided by, if you have a negative 2 here, you're going to square that. That's going to turn into a positive 4. 4 minus 1 is positive. Positive to the third power is still positive. So negative times positive is negative. Negative over positive is still negative. Negative, if you plug in negative 1/2 in here, that's still going to give us negative. We already said that that's always positive. And then the bottom part, when you plug in negative 1, negative 1/2 here, that's going to give us negative, positive 1/4. 1/4 minus 1 is going to be negative. Negative to the third power is going to be negative. So this is negative over negative, positive. And then same thing with the 1/2. It's going to be a positive. Positive here, but this is going to be a positive. So this is going to be a positive. Second derivative for positive 2. Positive, positive, positive equals positive. Oh, this one is negative. I'm sorry. This one is negative, right? because when you plug in positive 1/2 here, that will give us 1/4. 1/4 minus 1 is negative. There you go. I'm sorry about that. All right, so we have negative, negative, positive, positive, negative, negative, positive, positive. So we have a function. This is decreasing, increasing, horizontal. Sorry, that's we're not looking at this. This is second derivative. So this is concave down, concave up, concave down, concave up. So this is concave up from -1 to 0, and from 1 to infinity. It's concave down from -infinity to -1, and from 0 to 1. All right, that looks good. Perfect. All right, and then let's go and jump into the next part. They're also asking us for an inflection point. So we do have a possible point of inflection. Well, actually, because this does not exist, right? That's not a inflection point. Also, same argument for this one, even though there's a change of concavity, but this number does not exist, right? We do have a change of concavity here. We go from concave up to concave down. So x equals 0. It's a possible point of inflection. So we have possibly a point of inflection at x equals 0. So we gotta plug it into the original function. The original function. Let me go back to my notes. It'll be f of x is x over x squared minus 1. So this will be 0 over 0 squared minus 1 is 0 over -1, which is 0. So 0.0 is going to be a point of inflection. Because there's a change of concavity there. And I think we got everything we need. Let me check, double check here. All right, so let's look at our notes. Perfect. All right, so let's start with what we found earlier. We know that we have an X-intercept, Y-intercept at the same place. So that's at x equals 0. Then we also know that we have a vertical asymptote at x equals 1 and -1. So we draw a asymptote, vertical asymptote at -1. We can say here x equals -1. And then here we also have a positive vertical, well, just a vertical asymptote at x equals 1. We also have a horizontal asymptote at y equals 0. And then, all right, so the next thing that we found was we know that the function is decreasing from -infinity to 1. So we know that it's decreasing in this direction. Also, we know it's decreasing here as well. And it's also decreasing here, right? So everything in those three intervals, the function is always decreasing. And then we also know that there's no local max, local min. And then we also have, we know that we have concavity, right? Concave down on the left side of -1. So we have concave down somewhere in here, concave up somewhere in here, in this area, concave down in this area, and concave down in this area. So we need to figure out how this is going to look like, right? Well, let's look at the first one. We know that this needs to be decreasing, but it also has to be a concave down. So if you think about it being up here, this means it's increasing, right? And this is concave up. So this is actually the opposite. So what about if we try the other one? What about this? This is actually decreasing and it's concave down, right? And remember that the function it sort of has like this magnet that it just gets attracted to it, right? So in other words here, we have found that this should be down here. We should have a function that goes from here like that. And the other one is decreasing. So let's see, this is decreasing. So we're gonna have decreasing here, and this concave up, right? So it's concave up. So it's decreasing. So if we notice here, in order for us to have a decreasing function, right, we need to be going down, but it has to be concave up. And that's actually looks like is decreasing, but it's concave up, right? So we cannot have this, right? Because that means it's increasing at the end. So what we're saying here is that this needs to be kind of like this, and then pass through here. There you go. And then in the next part, it says that it's decreasing on this side, but it's concave down. So something like this, right? Well, it cannot be like this because this part is increasing. So we have to stay with decreasing. So that means it's just going to be this part. Like that. And then, let's see if I can erase this part. And then lastly here, same thing. This needs to be decreasing in a concave down. Decreasing on concave down. So decreasing and concave concave up, right? Like this. So this is decreasing and concave up. If we put it over here, this is increasing and concave down. So that's actually opposite. So that means that our graph is going to look like this. There you go. And we want to label our point, our most important point, and that's all we needed to use, right? So if you notice, all the information that we used, that we found, was very helpful, right? And again, going back to the beginning of this video, the introduction of this section, we use the information that we have with f prime, and the f double prime to learn some of the characteristics of the function. These characteristics helps us identify and learn the behavior of the function, and will allow us to get information that is needed to be able